Hey everybody, we are moving towards the asynchronous component of the course, and this will be basically through the end of the course. Alright, so we're on chapter 13, which is alkynes. We already did some of the kind of conceptual details in the PowerPoint. I think it was number 1 was nomenclature. Number 2 was physical properties. Number 3 was spectroscopy. Primarily we were focusing on proton NMR spectroscopy. Right? So yeah, in each of my lectures I usually try to break it down into little points, and they pretty much are consistent with the book. Sometimes I might skip a section, but anyway, it kind of helps you in your notes, and I definitely recommend all of these kind of whiteboard style lectures that you should be taking careful notes. Maybe recopy your notes. Maybe use 2 colors. Sometimes I'm going to use a combination of blue and black, like for my mechanisms and stuff. So anyway, alright, cool. So the first thing is how do you make alkynes? Preparation of alkynes. And a lot of these chapters, what we'll do is we'll say, like, how do you, for a functional group, how do you make it, and then like what can you do with it? So like preparations of blah blah blah, reactions of blah blah blah. So we're going to see that here. The first way to make alkyne is through the double elimination. Of a 1,2 dihalide. And by 1,2 dihalide, we kind of mean like a bromide or something like that, right? Okay, so what do we mean by this? And I'll go through the whole process, basic idea. And this uses a little bit of your alkene knowledge. So the basic idea would be, if I have an alkene, just for an example, say I have an alkene and I react with Br2. Okay, and what does that do? It makes the dibromide, right? It goes bromine, bromine. It's one of the alkene reactions from chapter 12. Well, but anyway, and if we react first with Br2 and then like a base, a strong base like E2, elimination base like NaNH2. NaNH2 is the base we're going to use, so Br2 and then NaNH2. Then we can essentially generate an alkyne. So this is one of the ways we can make an alkyne. Is take an alkene, dibrominate it, and then react with base, and it does this double elimination thing. Alright, so let's see what that looks like. So the mechanism for the first reaction is kind of an organic 1 reaction from alkene chapter. So the alkene attacks Br2, kicks off a Br, a second Br, and then we get this thing. Do you remember what that's called? It's a weird cyclic bromine type thing. It was called a, looks like an epoxide almost with the oxygen, but it's a bromine. It's called a cyclic bromonium. Cyclic Bromonium. It's got the same kind of character as a epoxide in a lot of ways. Anyway, so then Br minus, which you created Br minus up top, it attacks and opens it up, and now you get a 1,2 dibromide. Okay, so what happens to the 1,2 dibromide? Now we use our base, which is NaNH2. I'll just say NH2 minus. Alright. Sometimes I also abbreviate the base as just B dot dot, right? Like B dot dot, you know, it's a base with a lone pair that can attack protons and stuff. Anyway, this is just going to do a E2 reaction. E2 reaction. So, base takes the proton, kicks off a Br. What does that give you? You got the other Br still. You have so there's two BRs, right? And so we kick off one BR, the other one, you know, the stereochemistry can be kind of back and forth, but the other bromine is still there on this right side carbon, and then we just do it again. So that's really all there is to it. NH2 minus, H2N minus this time. So it's H2N minus, and now it just does the same exact thing again. And so it's essentially a double elimination. You eliminate once, you eliminate twice, and now you have an alkyne, right? That was it. There's the mechanism. I think I mentioned earlier, I would recommend, you know, if you haven't started doing index cards for reactions, now's a good time to start, where you might do like the kind of like the reaction reagents and stuff on the front side of the index card, then the full mechanism on the back, and you can kind of quiz yourself and remind yourself how it works. Okay. Alright, so let's show another example. What if we have benzene with two alkenes? What happens if we react with Br2 and NaNH2? What do you get? You get the dialkyne. Another thing about alkynes is first of all, remember there's two carbons there. There's two carbons there. This is also like two carbons and two carbons, right? Carbon, 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 carbon. But the other thing is, alkynes are linear, remember, because of sp hybridization. So you have to draw them kind of this way, of like, you know, like carbon, 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 and then the hydrogen's out here. It's a linear functional group. Pet peeve is sometimes people will draw an alkyne like, we'll say like this or something like that, and that's totally wrong. Totally wrong. You'll get a point deduction for that. Alkynes are not bent, and if you, on your quizzes or homework or whatever, you, well, if we ever leave you a comment that says bent alkyne and I take points off, now you know what a bent alkyne is. Bent alkynes are bad. This is a bent alkyne. And there's no such thing as a bent alkyne, so when you draw a bent alkyne, you get points taken off. I don't know how many points it'll be, but okay. Anyway, so and what's the intermediate? There's no way, I'm not going to draw the full mechanism, but clearly, when the alkenes react with Br2, what do you get? Dibromide here. Dibromide there, and then you get the double elimination, you get the alkyne. Alright, so key mechanistic and intermediate. I'm not going to go through all the mechanism for this. Anything else to say? What's the mechanism of this step? The first one is that E2 reaction. The second step is not necessarily an E2. It looks like an E2, kind of, but with the alkene, it's not actually a traditional E2 reaction. Absolutely the first step is, though. Okay? Another little note. When in that second elimination, because there's two eliminations, right? In the second elimination, cis and trans alkenes both work. What do I mean by that? Because if you remember, in a normal E2 reaction, normal E2, like if you have a base and the bromine comes off, there's this thing called anti-periplanar. So the base, this is back several chapters ago, but the idea that when the base takes off the proton and kicks off the leaving group, that there's a 180-degree relationship between the proton and the leaving group, right? We say must be anti-periplanar. That was something you learned when you learned about E2 reactions. But anyway, in this, we'll say alkenyl elimination, the second step of our reaction here, alkenyl means alkene. It can either be, it doesn't have to be anti-periplanar. That's all I'm trying to say. So if you have this is cis. Well, I mean, the relationship between the hydrogen and the bromine is cis, I guess you'd say. They don't have to be 180 degrees. You don't need this anti-periplanar relationship. So this actually works also. And you get the alkyne. A nice linear alkyne. Don't drop into alkynes, okay? So yeah, it just takes the proton. Whether or not it's a concerted mechanism is not that, you know, like I'm showing, pulling off the proton, making the triple bond, kicking off the leaving group. Whether or not that's all concerted, that's, you know, there's other ways to draw this mechanism as well. We don't care about that level of detail here, though. Alright, so let's see. Alright, so we learned the double elimination method to make alkynes. Now we'll do the next one. Okay, so the other way, the other main way to make alkynes, we'll call it number 5, is via preparation of alkynes via alkynyl anions. Alkynyl anions, okay? What does that mean? Well, we learned about that in the PowerPoint presentation. Recall that alkynes and terminal alkynes, so it's an alkyne at the end of a chain, have a kind of acidic proton, right? So it's what did we say the pKa was? It was, I think it was like 25-ish or so. pKa, I think around 25-ish or so. But anyway, it's relatively low when you think about the pKa of like alkanes. It's like 60 or something. 25 is pretty low, and so we can take off that proton with typical base. We would use is also NaNH2. That's convenient. So we can just draw NaNH2 as Na plus NH2 minus, 2 lone pairs of nitrogen, and yeah, it just rips off the proton. We call it a synthetically accessible deprotonation. Synthetically accessible deprotonation. What does that give us? Rip off the proton. We're left with an anion. Notice again how I'm drawing my alkyne. It's like not bent. It's like a benzene, CH2, CH2, and then we have a alkyne, nice linear. It's like, you know, that's 180 degrees from that, etc. Alright, there we go. And what's the counter ion on the carbanion, Na plus. Cool. Alright, so this is a good nucleophile. And being a good nucleophile, I can throw in maybe an electrophile. We're gonna just use alkyl halides right now. So Br, like a 1-bromo-propane or something like that. And so yeah, it just does an SN2 reaction. This is an example where you can do SN2. The carbon attacks this carbon, kicks it off. What's the partial charges here? It's delta minus delta plus, right? On the carbon with the bromine. So where's the minus attack? On the delta plus carbon, right? So circle and pair, attack, kick off the Br, and what do you got? Now you just built a new molecule. Something like that, right? Alright, so what's the mechanism of that? There's a name for this, 3 letters. What is it? Something something 2? This is an SN2 reaction, which is, right, it's bimolecular nucleophilic substitution. Meaning, if I increase this or I increase this, the rate increases. Both of these are involved in the transition state. It's just a standard SN2 reaction. Alright. There's a requirement, though. Requirement for this to happen, for this nice beautiful SN2 reaction to happen. I don't know if you remember this from the SN2 chapter, and you know we learned about elimination, but that basically that SN2 can compete with a reaction. Like sometimes SN2 works great, but sometimes if these are bulky or something, another thing happens. What is it? Another thing that has a 2 in it. It's elimination, and that's where rather than be a nucleophile, this will just be a base. Base itself. It'll be a base and it'll pull off the neighboring proton and make an alkene, right? That's called E2 reaction. So I guess the question is, the requirement is, what kind of substrates can I attack in order for it to do an SN2, and when might this, if the substrate is maybe has some other property, when might it do E2? Does that make sense? It's like, when is it going to be SN2? When's it going to be E2? And we talked about this before in Organic 1 also. It was like the substrate requirements for some SN2 reactions. But anyway, the requirement is simple. Rx, which is the alkyl halide, Rx, it's got to be, must be primary or methyl. It's got to be primary, it's got to be methyl. If it's not primary or methyl, like if it's secondary or tertiary, otherwise, you know, like for secondary or tertiary, you get E2. Otherwise, E2 occurs. Okay, so if you use a primary methyl, SN2 occurs. And I mean, typically, the goal, if you're trying to build a molecule here, is not to cause elimination, but SN2. E2 is kind of like a undesired side effect. So, as an example, if I have bromocyclohexane, and I really want to make like this molecule, I'm like, all I want to do is kick off that leaving group with this propynyl anion. Butynyl anion. There's 4 carbons, right? I'm like, I want this to kick that off, right? SN2. I want this to attack. But the problem is it's secondary. So what we're trying to do here, kick it off, will not happen. Will not happen. What actually happens instead, is an E2. And how can I draw the E2, and what's the E2 product? You know, and I'm also, this is okay to draw what this is. Sometimes I actually like to draw the carbon more explicitly, so let's do that. Because it's a little weird with the little lines and the dots and everything. So I'm just going to draw this as an alternatively like this. Ooh, I almost drew a bent alkyne. Don't do bent alkynes, right? They gotta be linear. Okay, something like this. All right. So now we have a dot. Now I'm just drawing the carbons more explicitly. Okay. So what actually happens is elimination. So how do I do the elimination? Well, that would just be this grabs this proton, kicks this off, and you don't make what you want. We actually make an alkene. And now the alkyne just has a proton on it. So you totally did not get what you wanted. You did not get what you want. You didn't get the SN2 product. You got an E2 product. Okay. Just I'm gonna try to sneak it in over here, like on the left now. What if I really wanted this though? I really need this molecule. It's to make a cancer drug or something. How could I do this by a different route? How is there another way I could possibly build it? Well, if I can get this, and there might be other ways I can get this molecule. If I can get the alkyne with a cyclohexane on it, how else could I build this? Well, I could just do this. I'll let you make a guess. How could I do it? How could I actually just snap on an ethyl group and not cause any problems? Because this is just a matter of, you know, we have this great method, you know, use a base, take off a proton, and then attack something. Well, why don't I just attach the ethyl group? And I'll even draw a squiggly line of, like, you know, if this is what I want, why don't I just attach ethyl right there? And I can totally do that. How do I do that? That's actually not a problem. What do I do? How do I attach that ethyl group on there? Well, use a base, NaH2. And now at this point it's just I need to attach a 2-carbon piece. It's that, a 2-carbon piece with a leaving group on it, so bromoethane. Right, that would do it. Base takes proton, it makes an alkynyl anion, and then the alkynyl anion attacks bromoethane and you get the product. Okay? Cool. Okay, what else can we do with these alkynyl anions? So, also, what else can we do with them? Remember, so anions, carbanions, right? Carbanions is a carbon with a negative charge. We learned a ton about those at the end of Organic 1, right? Different kind of anions, but like, remember Grignards? Grignards and organolithiums, those are all carbons with a negative charge on them. Remember all that stuff? Well, those are similar, and these alkynyl anions are similar to those. So we can also react with ketones. What other things do Grignards react with? Grignards react with what? Ketones? What else? Aldehydes? What else? Anything else you learned from Organic 1? Other electrophiles that we can attack with a Grignard or Carbanion? Epoxides, remember those? So ketones, aldehydes, epoxides. Remember, all of these things are things we can attack with a organolithium, or carbanion, right? Okay, so example. Take an alkyne. How do we rip off that proton? We can use NaNH2. We can also use butyllithium. Butyllithium is a super duper base. It's one of the strongest bases in the universe. And rip off that proton, and now we have. How do I draw it? Again, I could either draw like CC, or I could just keep this like triple bond and draw the lone pair clearly. Maybe draw lithium plus. Another way to draw that, because I can draw it kind of ionically. I can also draw it kind of covalently. In reality, it's kind of a little bit of this, a little bit of that. But both of these are both ways I could draw this intermediate, this carbanion-like intermediate. Well, what happens if I react this with ketone? What happens? What do I get? It's just like it's like a Grignard, right? What's the well, I'll step through the mechanism and draw the product. But yeah, it's just this is a super duper nucleophile. That's a nice electrophile. So yeah, I like to draw circles around the lone pairs. Attack, form a bond, form a CC bond, right? And now what do we got? So we have now a OH methyl ethyl. Whoops, it's not an OH yet. It's O minus, right? Until what happens? And I'll put brackets around this. H2O. We protonate the O minus, and now what do we have? The final product. Ethyl, methyl and ethyl. Methyl and ethyl, okay? Make sure I draw my nice alkyne. Make sure you understand the meaning of this structure. Of course, it's carbon, 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 carbon. So how many carbons are there? 3, 4, 5, 6, 7, 8, 9. 9 carbons, right? That's the final product. Okay, that's a reaction with the ketone. This time I will try a simpler alkyne. Let's do NaNH2. Let's try, oh yeah, this is just another thing I like to draw. When I have a product like this, the last product, I draw a squiggly line, like right there. And that is helpful to show, like, well, where the bond was that we created. It was between this carbon and this carbon, right? It was a CC bond we created there. And also, when you look at this, and I see the squiggly line and where it is relative to the OH, I'm like, and the fact that it's a tertiary alcohol. This is a tertiary alcohol, right? I can be like, well, this is obviously created from a ketone. I can, where the squiggly line is, and also the nature of the alcohol, I can be like, that it was made from a ketone. What's the structure of the ketone? Well, of course, there it is. There's the ketone, right? So anyway, the squiggly line helps you. Alright, so this next example, NaNH2. Let's try an aldehyde. Okay, so simple aldehyde, and let's throw in the water step also. I'm going to skip all the mechanism and just jump to the product. You can draw the mechanism. How many carbons total here? 1, 2, 3, 4, 5, 6, 7, right? There's a carbon, there's a carbon. And I think some students have difficulty seeing that. So make sure you can count 7. 1, 2, 3, 4, 5, 6, 7. C7. Okay, and where's the squiggly line that we created? The bond we created, it's right there. There's a squiggly line, right? Cool. And of course, looking at just the product and where the squiggly line is, I should be able to look at the product and see the squiggly line relative to the OH, secondary alcohol, and when you see that, you say, oh, that was created from an aldehyde. What aldehyde was it created from? Oh, that aldehyde, right? But I just by looking at the squiggly line and where the OH is, I can see that. Okay. How about, let's change it a little bit now, alkyne, a terminal alkyne with the ethyl. Let's try, oh yeah, and I also, just for your notes, I recommend you do the mechanism down here. Yeah, go through that mechanism. Okay, so for this one, what base should we use? Right now, you know 2 bases, right? Give myself more space. Okay, what are the 2 bases we're using for alkynes? Butyl lithium, 4 carbons lithium, or NaNH2. So we can take our pick. I'll go back to butyl lithium. Not much of a difference in terms of the applicability of those. Let's pick an aldehyde, an epoxide now. Okay, so I'm going to let you do the mechanism, but basically what is the mechanism? The alkyl lithium, circle the bond, it attacks, kicks the proton, kicks the electrons onto the alkyne, makes an alkynyl anion, 1, 2, 3, 4 carbons, right? 1, 2, 3, 4. And that 4 carbon piece will attack. And which side would do basic nucleophiles, because it's definitely basic, it's not acidic. Which side of an epoxide will it attack? Is it going to attack the left unhindered side or the right more hindered side? It's always going to attack the left unhindered side. So it's going to attack, this carbon's going to attack that carbon, break it open. And I'm not going to review this from Organic 1, but there are cases where nucleophiles will attack the more hindered side. So you can review that as Chapter 9. I think it's like acidic nucleophiles. This is a non-acidic nucleophile. It's actually kind of a basic nucleophile. But if you have like HBr, for example, HBr would react in a way that the Br would wind up on the more substitute side, because that's due to carbocations, right? Okay, I'm just going to draw the product. Okay, so now this carbon is connected to this carbon, so we have the carbon. And there we go. And where's our squiggly line? Squiggly line is right there, and that the relationship of the squiggly line, because that's the bond that was created, and to where the OH is, suggests the nature of the electrophile, right? It was, did we attack a ketone, an aldehyde, or an epoxide? Well, of course, it should be in your short-term memory right now. Of course, we attacked an epoxide, and the part of the way we know we attacked an epoxide is the squiggly line is 1 carbon away from the OH. Okay. Cool. Alright, so we're going to do a quiz slash exam style synthesis problem. Quiz/exam style synthesis problem. So if I have like a 2-carbon alkyne, what's the name of that one? It's, of course, it's called ethyne, like ethane, but with a Y. Well, it's also called acetylene, right? So the names of this are ethyne or acetylene. And I'm like, how could I take this molecule and attach, we'll say, benzyl, which is benzene CH2. The pH is just an abbreviation for a benzene, right? And maybe a alcohol on the other side. Okay, so how can I do this synthetically? It's a synthesis style problem. It's like I gotta attach some stuff. What do I do strategically? Remember, you need to be able to understand the structure of this and where the, you know, what carbons are there. What carbons are there? Well, there's 2 there. This is, ignoring the benzene, it's like 1, 2, 3, 4, 5, 6, right? 6 carbons. So when I do a synthesis, I look at the product and I look at the starting material and I think about like squiggly lines. Draw some squigglies. Well, here's a squiggly and here's a squiggly. So obviously we're attaching one thing and we're attaching another thing. And the other thing is looking at the right. This is easy, right? This is just a benzene CH2, maybe like a BR, like a leaving group, right? This alcohol, right now, you know 3 ways to do it. You can do ketones, aldehydes, and epoxides, right? Ketones, aldehydes, and epoxides. And so when you look at this, and you look at the relationship of the squiggly to where the alcohol is, I hope you're able to say, well, it's not a ketone, because a ketone would have the alcohol right there. And additionally, if it was a ketone and the alcohol was right here, you'd have an extra like R group, like a methyl or something, right? Okay? Because ketone, when you attack a ketone, you always make a tertiary alcohol, right? So it's not a ketone, it's not an aldehyde, because an aldehyde would also have the OH right over here. So what is the third option? Epoxide. So this is like the thing that this carbon's going to attack will be like a 3-carbon epoxide. So carbon, carbon, carbon epoxide, right? Okay. So now we have a strategy. First step is develop a strategy. Second step is implement the strategy. So I say, epoxide. Epoxide. That's like part of our strategy. Say epoxide, epoxide, epoxide. Okay. So what is the actual synthesis? I'll go backwards. Now, retrosynthesis, right? Which thing should I attach first, strategically? Should I first attach the benzyl group, the benzene CH2? Or should what did I say, benzyl? You don't know that word. Maybe you know that word. Benzyl. B-E-N-Z-Y-L. Definition of benzyl is not the benzene, it's the benzene and the CH2. So benzyl, you can Google it or Wikipedia search it. Benzyl, definition of benzyl is benzene CH2. Okay, so should we attach the benzyl first or attach the alcohol thing from the epoxide? Strategically, does it make sense? I think it makes sense to attach the benzyl thing first. First attach this, because if we attach the alcohol first, then we have to worry about like that alcohol functional group, and like, you know, if we attach the alcohol first, then the alcohol is kind of in the way for maybe doing the second reaction, which is attachment of the benzyl. So strategically it makes sense. Let's just get this one out of the way because it's really simple. to attach first. So I'll go backwards though. Putting it all together, if we're going to attach the epoxide second, then we're going to assume we have the benzyl already on. Right? Assuming the benzyl is already on the alkyne, we'll do that as we work our way backwards. Then it's just a matter of a 1, a 2, and a 3, I think. It's going to be a 3-step process to attach the epoxide. Step 1, base. Step 3 is water, because you need a proton for the alcohol. So water. Pick a base. What's your base? I don't know, NH2. Sure. Okay, what's our electrophile? What do we say? It's an epoxide. How many carbons is the epoxide? 3. It's a 3-carbon epoxide. That's it. Base takes off the proton, makes a carbanion, C negative, and the negative carbon attacks the epoxide, opens it up, right? Opens out, so the carbon, the C minus attacks the carbon, breaks open the epoxide, right? And that makes the O minus, and then O minus grabs this proton. If you are confused by that, step through the mechanism yourself. Yeah, or come to office hours. The other thing is, in a synthesis problem, you don't go through the mechanism. A lot of students say, "Oh, I have to do mechanisms everywhere, everywhere, everywhere." Well, certainly on a quiz or exam type problem, you don't do a mechanism unless I say draw a mechanism. So there's no mechanism here. I'm just saying reagents: base, electrophile, water. Okay. So when I say step through mechanism, I mean, like, if you are unclear on this mechanism, you should draw it out yourself somewhere on your paper of how this works. Okay. Now this is super easy. How do we do this? Well, this is even easier. It's just 1, 2. Take off a proton. We'll use NH2 again. What's the electrophile? Maybe we'll draw it another squiggly. There's the squiggly. Cover up everything that's not changing. So it's benzene or pH, CH2, and then what kind of leaving group do you like? Usually Br, bromide. Cool. Nice little short synthesis problem that puts together the kind of attacking alkyl halides and attacking like epoxides to make alcohols. Alright. Alright, so what did we just learn about? We talked about alkynyl anions, right? We can rip off the proton and go attack electrophiles and stuff. Let's, as one of the reactions you can do to alkynes, let's talk about reduction of alkynes. Reduction of alkynes. Reduction of alkynes. And there's going to be 3 ways to do this. And these are kind of related to, if you remember, Chapter 12, reduction of alkenes. Remember reduction of alkenes? So if you take a alkene and I react it with something, I get, here, let's do 4-carbon alkene as an example. And I go to a 4-carbon alkane. How do you do that? That's Chapter 12. Chapter 12. How do you do it? It looks like you're adding H's, right? CH, and there's like CH2, CH2, so you're adding H's, so it's H2, palladium on carbon. That's how you reduce an alkene. So let's talk about reduction of alkynes. There's 3 ways to do it. Way number 1, way number 2, way number 3. So the first way is just going to be identical to alkene reduction. H2, Palladium. Oh yeah, what is this C? What does C mean again here? PD/C, Palladium on carbon. What that means is that Palladium is a metal, and it's kind of absorbed onto carbon, so essentially charcoal. And this stuff looks like charcoal. It's like a black powder, right? Okay, so 3 ways to do alkyne reduction. You can do H2 and like palladium on carbon or platinum on carbon, usually. And that's going to be called a full reduction. Full reduction. Alright, good. We cool so far? And now we have 2 more. We have H2 and a special catalyst called Lindlar catalyst. I'll define that in a second. Full reduction, means like a double reduction, because you have 2 double bonds, right? This is going to be a full reduction. This is going to be a partial reduction. And your product's going to be cis. So I'll explain that in a second. It's a partial reduction, and you're to basically alkyne. You basically make an alkene, right? It's partial reduction, and it's going to give a cis product. And then the third one is going to be typically it's going to be sodium and ammonia. Sodium ammonia. Sometimes you use lithium, like sodium or lithium, and it's NH3. And this is going to be a partial reduction. And what's the opposite of cis? It's going to make trans. The trans favored. If you have stereochemistry in the alkene that you make, second method would make it a cis alkene, and the third method would make it a trans alkene. Okay, so that's a summary of all the things we're going to do. There's full reduction, partial reduction, and another partial reduction. Another thing, what was the base we were using, like last topic? It was what? Na. There's butyllithium, and there's the ones like Na, NH something, NaNH2, right? But this is NaNH3. This is like 2 different molecules. You got a metal and you have NH3. So a common mistake in this chapter is people like confuse the concept of a base being NaNH2 with Na and NH3 as 2 different reagents. Alright? So just don't make that mistake. Okay. So what's the full reduction? Full. I'm just going to draw a miscellaneous alkyne. Make sure you draw it nicely. How many carbons are in this alkyne? 1, 2, 3, 4, 5, 6, 7, 8 carbons. What's the name of it? It's 1, 2, 3, 4. 1, 2, 3, 4 octine, right? Because 1, 2, 3, 4, 5, 6, 7, 8 carbons total. That's 4 octine. Let's react it with full reducing conditions. So what's that? Full reducing conditions, like H2 palladium on carbon, or H2 and platinum on carbon. So we'll do H2 palladium on carbon. And the full reduction is just going to completely reduce the alkyne all the way down to an alkane. How many carbon? Alkane. Well, this is oct, so this is octane, right? 8 octane. 1, 2, 3, 4, 5, 6, 7, 8. It's a full reduction. So H2 palladium just does a complete reduction. Okay. Let's see. Let's try a partial reduction now. Partial. And we're going to do the Lindlar first. Lindlar. catalyst. Now the mechanism of the alkyne reduction, it's a double reduction, right? You add H2 once, you add H2 twice. So it's not that exciting. We're basically going to skip it. It's kind of, if you look in chapter 12, the alkene chapter, it's kind of like how we described H2, palladium and carbon, reducing alkenes to alkanes. It's the same thing. It's not that exciting, so we're going to basically skip it. So we're going to focus a little bit more on the Lindlar and the other one, the sodium ammonia. Okay. So the Lindlar. What does Lindlar do? It makes cis alkenes. It reduces alkynes to cis alkenes. How does it do it? Let's draw a alkyne. Draw H2, Lindlar. I'll explain what Lindlar is in a second. It's the catalyst mixture. Lindlar cat. It converts the alkyne into a cis alkene. So what does a cis alkene look like? And how many carbons is it? Well, this is 1, 2, 3, 4, 5, 6. You call this 2-hexyne, right? 1, 2-hexyne. And it's just going to convert this 6-carbon alkyne into a 6-carbon alkene. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Uh-oh. 1, 2, 3, 4, 5, 6. Okay. C6 in, C6 out. Okay? And yeah. Alright, so, and I'll explain the mechanism, but it's essentially, even this mechanism is identical to the top mechanism. This H2 palladium style reduction. With the only difference being that this just stops halfway to the cis alkene. Okay, it just, like the second reduction is a little more difficult, and so the catalyst just stops working after the first reduction. This is a better catalyst, and so the good catalyst can easily add H2 once and then add H2 twice, and you get the alkane. Okay. All right. So what is Lindlar catalyst? It's a special formulation of stuff, some mixture of chemicals. It's palladium, I think complexed with or mixed up with calcium carbonate. It's like palladium metal mixed with calcium carbonate. It's got some lead in there, lead, Pb, lead acetate, which is equal to PbOAc2, PbOAc2, lead diacetate. It's also got some quinoline, which is a benzene, nitrogen. This stuff is called quinoline, quinoline, right? All right. So that's what Lindlar catalyst is. It's a mixture of these three chemicals. You obviously don't need to know that. Just remember Lindlar. And what does Lindlar do? It converts alkynes into cis alkenes. What are the names of these things again? This is 1, 2, 3, 4, 5, 6. 2-hexyne. What's the name of this? 1, 2, 3, 4, 5, 6. So it's 2-hexene. That's right. It's 2-hexene, right? Because it's ene. Goes ine to ene. And is it cis or trans? It's cis. 2-hexene. Cis 2-hexene. Okay. One more thing. We call it a special formulation. Lindlar catalyst. There's another name for this because it's weird. Because you know how it does a single reduction and stops on the second reduction, prevents the second reduction. there's a name for it. It's called a poisoned catalyst. I guess that's the historical nomenclature. It's a poisoned catalyst. And by poisoned, it sort of means it's slightly deactivated. So, causes a single reduction, not the second reduction. So, yeah, it only reduces one of the 2 pi bonds. Okay. Why is it cis? Why is product cis? Why is the product cis? And it's a Syn Addition. If you remember chapter 12 with alkenes, there's like 2 kinds of additions. There's Syn Addition versus anti-addition. Syn and anti, and it sort of depends on where the things get added across the double bond. And Syn Addition basically means they're going to be added on the same side, and of course when they're added on the same side it makes cis. So let's go through the mechanism. And this is kind of like how the H2 Palladium mechanism works too. Okay, so here's our catalyst, PD or whatever. Palladium, it's the, and Lindlar, whatever. It's the whole catalyst mixture. You have a surface. It's like a metallic surface. And what happens to H2 when it sees that metallic surface is it kind of attaches to the surface. Okay, kind of gets attached. And then our alkyne, I'll just draw this alkyne. Yeah, sure. There, that one. And it kind of sits underneath this surface with the H2 absorbed onto it. And then the addition actually happens like this, dot, 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 dot. That's going to be the electron movement, or like where the electrons are moving. And it's just going to be the opposite of kind of the attachment. It's just like this goes there, this goes there, this goes back onto the palladium. And it's 3 arrows. Now you got your catalyst back, ready for another reaction. And you got your, let's try to draw this carefully. There's our alkene with a cis added H's, right? I had to kind of pop down the 2 ethyl groups, and yeah, that's it. That is why the Lindlar adds to make cis products. The other question is, why doesn't it keep going like the way H2 Palladium does? What's special about Lindlar that makes it stop? I don't have a good answer for that. It's something about the, probably got to go ask Lindlar. I don't know when Lindlar was alive. Pretty sure he's not alive anymore. But anyway, this catalyst was kind of discovered by trial and error, I think, and they just started mixing chemicals up and found, okay, well, this special formulation will stop at the cis alkene, and then this is stable enough that it doesn't react the second time. So anyway, don't have a good explanation for why Lindlar doesn't continue to make this into the alkane. All right. Okay, and then the other question is the partial reduction that is trans-selective. Partial reduction via what are the reagents for this for the trans one? It's not H2 and it's not Lindlar and it's not palladium. It's what? The partial reduction via what? What's the thing that's trans-selective? Trans-selective. It's something else. It's not It's not NaNH2, it's NaNH3. And Na is metallic sodium, NH3 is ammonia, so this is a low temperature thing because it's kind of a gas, right? NH3 is a gas at room temp. So you got to cool this down to like negative 100 degrees, or maybe negative 80 or negative 100 degrees Celsius for this to actually work, because otherwise NH3 is a gas, right? Ammonia is a gas at room temp. So it's a very cold process. Cold, I don't know the exact temperature. Cold. But you would maybe use liquid nitrogen or something to cool down your reaction mixture to the right temperature. Okay, so what is the... Let's give an example and we'll do the mechanism. Here's an alkyne. Let's do NaNH3. And what's the product? Is it sister trans for the NaNH3? Sister trans. It's the trans one. So ethyl, right? Okay, so you make a trans alkene. Alright, so what's the mechanism? We explained how Lindlar worked. Lindlar worked because H2 was added to the catalyst and then it was delivered in a kind of syn manner to make this cis alkene. So then the question is, why do you get a trans alkene through this? It's a totally different mechanism, and that's why. Totally different mechanism. So let's do the mechanism now. First thing is sodium. If I say Na, are there any electrons around it? Is this like Na plus, like the cation? The answer is no. This is metallic sodium. So this stuff's insanely reactive. Sodium is insanely reactive. If this touches water, it just explodes, right? This is a super, super reactive chemical. And it has a free electron on it. It has a free electron on it. Alright? There's a free electron on it. And it wants to get rid of that electron. It really wants to get rid of that electron. And when this reacts with water to make H2 and a big fireball, it's due to it losing its electron. It's a reducing agent, right? Okay, so I'm going to use this in a kind of Fishhook-y radical style mechanism, which you learned about in Organic 1. So fishhooks, fishhook arrows. Are these fishhooks? Is that a fishhook? Those are not fishhooks. These are 2 electron movement arrows, right? So by a fishhook mechanism, I'm describing single electron movement. So I'm going to draw like a fishhook. So this can react with double and triple bonds. It's kind of like a radical. It's kind of like a radical. It's got this single electron. It's going to react kind of like a carbon radical or something. And radicals react with double bonds and triple bonds. So it sees a triple bond. Fishhook reacts. I'm going to have a second fishhook that kind of goes there from the triple bond. So we're basically forming a bond from sodium to carbon. Okay, and then a third fishhook where the bond breaks to make a carbon radical on this carbon. So this carbon will have a dot. This carbon will now be connected to the sodium. So what does that look like? Sodium, ethyl. Alright, sodium attached. And we have a alkenyl carbon radical now. Sodium attached. You might remember that, like, is this a happy molecule or a unhappy molecule? Well, you got a radical, so it's kind of unhappy. It's also kind of unhappy because the carbon-sodium bond, that's like a organolithium or like a Grignard, right? That's super unhappy and super reactive. So this is kind of the same as, kind of like carbon dot dot negative ethyl sodium plus, right? It's a carbanion. With brackets around it. It's like a carbanion type molecule. All right, and now being a carbanion type molecule, does it like that? And is it content? Like, does it maybe want to get a proton? And yes, it's just like a Grignard or organolithium or organosodium. These things would rather get a proton from somewhere. So it can react with ammonia, NH3, in an acid-base like reaction. So this is going to be a super base. Well, we got a proton that can be provided. So this is just going to rip off that proton. The C- is going to grab a proton off ammonia because you got lots of ammonia, right? So now I'm just going to kind of circle this and go grab the proton. Okay, good. Molecule's a little happier now. It just got rid of the whole carbon negative thing, which is just like a very unstable thing. You know, it turns out that this carbon with the alkene with a radical on it is it doesn't really have stereochemistry, so it's probably best to draw it kind of linear. I do a little bit of an angle there. That's not exactly true. I think it's actually a little more linear. Whatever, it's not a big deal. But yeah, it's a radical on the carbon. This is still unhappy also. It's not like we've solved all the instability. So we still got this guy. All right, and now a couple more steps here, and our final product will be the trans-alkene. That's the final product, right? Now sodium. We still got sodium dot around. There's a lot of sodium dot. Now the sodium dot and the carbon dot are just going to form a bond. So sodium dot goes fishhook, fishhook. So fishhook, fishhook, and they form a covalent bond. Okay. Okay, and what does that look like now? It's kind of like, actually let's redraw this. I'm going to draw the carbons explicitly. Carbon, we have a H, we got ethyl, we got a carbon, and now when the sodium attaches, it's also kind of either covalent, it's a little bit of covalent character and a little bit of ionic character. So I'm just going to draw it kind of as like ethyl ... and Na+. Okay, you could either draw it kind of in a sort of covalent fashion or this sort of ionic fashion. Okay. For our mechanism, though, it helps to just kind of focus on this sort of ionic type fashion. All right, so now we have now another carbanion, right? Another carbanion. The other thing about these intermediates is that they are kind of, the stereochemistry is sort of undefined, but they are trying to eliminate clashing. Like the two ethyls want to be kind of far apart from each other. So there's a, right, it's not like a fixed locked stereochemistry, and that's why the end product is going to be trans, right? The end product we know is trans, and we know trans is actually stable, right? This is actually the most stable alkene you could draw. That is the reason why the trans is going to be favored, is because of all this kind of, non-locked behavior of the intermediates. All right, so we have this now, and what do you think is going to happen now? Same thing as before, right? Super unhappy carbanion. Oh, we have a proton source. We have a proton source. So what's it going to do? Take that proton off, and we're done. we have our transalkene. I just drew the ethyl groups a little bit differently, but it's the same product. These are the same molecule, and we're done. That's how you get this kind of reduction, trans-selective reduction with sodium ammonia, which is cool. I'll state that in a couple words down here too. All right, so let's just summarize this last reaction. The trans selective partial reduction of a alkyne to the transalkene. So let's say this in a couple words. Why is it trans? Why is the product trans? Question mark. Why is the product trans? And the answer is the radical intermediates have an opportunity to equilibrate to most stable stereochem. Alright, so what that basically means is that these are not locked. These intermediates are not locked in their configuration, and so in the end forming the most stable alkene is possible because we don't have a defined stereochemistry. Okay, and they equilibrate such that to form the most stable product. Okay, and that's how we get the trans product. Okay, so basically done for today. I'm just going to say, let's summarize those three methods real quick. Three methods to reduce alkynes. Reduce. Three methods to reduce alkynes. And what are the three methods? And we'll just draw some random alkyne. Just add a methyl for fun on the end. Okay, so we have three methods. H2 palladium on carbon, H2 Lindlar, catalyst, and then like sodium or lithium and H3. They both do the same thing. Sodium or lithium and ammonia. And yeah, so what are the products? H2 palladium on carbon does a full reduction, so down to the alkane. So, and then we have how many carbons off here? 1, 2, 3, 4. 1, 2, 3, 4. You just get the alkane. All right. H2 Lindlar is going to convert the alkyne into a, was it cis or transalkene? Cis or transalkene? What do you think? It's going to be a cis alkene. There's our cis alkene. And sodium or lithium and ammonia makes a cis or transalkene. Makes a transalkene. So the H's are on opposite sides. That is a summary of those three methods. I think we're going to stop now. Okay, so yeah, we got through some cool stuff. We showed kind of how to make alkynes by a couple methods. Double elimination, we showed how to do the alkynyl anion method, and now we're showing some of the reactions like reduction of alkynes. Alright, we'll continue next time.